Hi, welcome to this class. We're going to wrap up chapter 6 about differentiation of measures and functions. We're going to get the Rolls-Royce version of the fundamental theorem of analysis in place and a few other nice things. So let's recapitulate a bit where we were. We had introduced, given a measure on RD, a finite one, but I'm working on the realigned rule for simplicity. This was it, right? You do the lim sup of this quotient here. You do that at every point x, and you look at the intervals that contain the point x and are smaller than delta. Delta is where the limit taken. And then you do the same for the lim in. So no changes. And then we want to establish that this one and this one are actually equal almost everywhere, that equals the Radon coordinate derivative of the absolutely continuous part, so on. And where were we? We have actually, we had with great difficulty established that if the mu of x was bigger than or equal to some a, turns out I forgot to put a bar on this guy, I hope you didn't notice. For all x in some set big A, then mu of A was in fact bigger than or equal to A times lambda of A, which seems like a completely natural thing if you look at this definition, yeah? So if this is bigger than or equal to A for every interval and then for every x, I mean, then yeah, basically almost the same thing, take the quotient of this. You have, it's just here you have intervals, here you have some arbitrary set A. Anyway, very difficult proof, very beautiful proof where we use the Vitali covering theory. And then this one looked a bit differently. So yada, 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 and the conclusion is the same. U of A, well, except that inequality changes direction, but this dot, 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 dot have a plus to it. And this is not true unless we assume absolute continuity. And that's exercise 4 in the book, asks you to check that. But it turns out that exercise 2 in the book provides such an example. So work out the details yourselves. Basically, okay, I'll tell you. So the exercise 2 says, consider a line between the origin and the point 1, point 1. And then you take Lebesgue measure along this. So any set A, you look at the intersection of A with this line, and you just measure the one-dimensional Lebesgue measure there. That's your measure. Okay? Now, so if you want to look at what is the lim inf, you know, both these guys are identically 0 for any point x of this line. If we're on the line, so if x is here, then of course, if I want to minimize this quotient, I'm just going to take a square. So we're in R2 now, so the corresponding of intervals are squares. All right, so here I get 0 upstairs and delta square downstairs if the side length here is delta. So the limit here is going to be 0, so we get that the mu of x, the lower derivative is 0 everywhere. Now, if you want to maximize this instead, then move your square so that it has maximal intersection with the diagonal. Now, upstairs, you're going to get, in this definition here, upstairs, you get square root of 2 times delta, because that's the length, delta is the side length. And downstairs, you get delta square. And now you do a lim of that as delta goes to 0, and you get infinity, right? So for all x on the line, you have infinity. Okay, right. So this is always true because no matter, you know, if a is a positive number, then this a must be, it can be any subset now of this diagonal line. But every time I have a point outside, then this will be violated, right? So, and if I have a subset now of this diagonal line, I'm going to get 0 here, no matter what is little a, and I'm going to get well, some positive number. So that's fine. We look at this guy. Of course, here you can put any a bigger than or equal to 0. So let's put 0, and the right hand side becomes 0, no matter how you pick your a. But the left hand side can be positive numbers. Why? Because this measure mu is clearly not absolutely continuous. On the opposite, it's a singular measure by itself. It doesn't have an absolutely continuous part. Right? But the support where it lives is this diagonal line, which has measure 0 in Lebesgue. Okay, so yeah, that was just a detour. This is where we were. We have these two guys. Now we want to prove that they are identical almost everywhere. So in this case, they're identically equal to 0 everywhere outside this line. 0 is also the Radon conjugate derivative. So, you know, then those are equal almost everywhere. What we still haven't shown is actually the fact that these two are measurable, which of course we need. So let's start with that. This is done early in the book, so I shifted things around a bit. First observation here. Okay, so always when we work with Vitali coverings, we assume that these cubes or intervals or whatever are closed, and we use that in the construction of the Vitali covering theorem, yada yada, because you know, you remember we had intervals, and then we considered the remaining points. And those were always at some finite distance to the intervals we had removed already. And we know that because the intervals we were working with were closed. Otherwise, with open intervals, you could get some boundary points, right? And then you have a problem. But now we need actually to flip this around. We need to work with open intervals instead of closed in this argument. And you will see shortly why. But then the first observation is that if I do the lim sup here with either closed or open intervals, it doesn't matter. Yeah. And the reason for that is, okay, let's say if you have the real line and an interval here, you can always add, you know, a distance 1 over k and a minus 1 over k here to get an open interval, which is a bit bigger, right? Or given an open interval, you can always subtract a 1 over k. K is just a fixed integer, and get a smaller closed interval. And then when you take a limit process, you can approximate open intervals as an infinite union from the inside of closed ones as an infinite intersection from the outside of open ones, right? So
given a fixed interval I, we can always write it as an infinite intersection of open UKs, which are bigger, given an open U, we can write it as an infinite union of closed IKs, which are smaller.
Now, this guy is always finite, so we can use both lemma 1 to 5 and 1 to 6, lemma proposition, I don't know, saying that, you know, the limit of mu applied to this is mu applied to that, or lambda applied to this, lambda applied to that, and so on. So
we always have, for example, u of I divided by lambda of I. That's the same as the limit of k goes to infinity, u of uk divided by u of ik. Sorry, uk again.
Lambda, right? Using lemma 1 to 6. And similarly, yeah, k goes to infinity again. So with this, it's clear that if I use closed ones in the definition here, I can get arbitrarily closed all this with a similar quotient with open sets, right? So if I do the lim sup with the open ones, it's at least going to be bigger. But then if I consider the lim sup with the open ones, I can get arbitrarily closed using closed ones, and then that lim sup is bigger again. So, you know, then they are the same, like that here. So it's also okay to consider them to be open. We don't get a different definition in terms of these two functions here. Okay, I think this is, yes, lemma 2.2, 6.2.2. These three guys are measurable. Now, of course, let's remember what is this. This is the function which is equal to either one of these two on the set where they coincide and 0 elsewhere. That 0 set is negligible, but we don't know that yet. But that doesn't matter because from 2.1, where we studied measurability of functions, you know that if two functions are measurable, in this case these two, the set where they are equal is a measurable set. And then, yeah, if you set the function 0 outside of that, then so this guy is trivially measurable once we see that these guys are measurable. Now here in the book, they complicate things a little bit because they insist on checking, they want to prove that this set is measurable. If we do that for all A, then we're done, right, in terms of showing that he is measurable. But there are a number of equivalent conditions one can check, right? This also goes back to 2.1 in the book. So if I check this one, then again, if this is true for all A, then this function here is measurable. So I want to check that this is, well, to be more concrete, I want to check that this is in the Borel sigma algebra, right? So how do I do that? Now, let's call this set now A, or let's call it E. So there's an A there. Okay, so first consider the collection of intervals of length less than 1 over k, k is a fixed integer, such that this quotient is bigger than A, right? So if X is in this set, then we can always find an interval I, as long as k is big enough, we can find such, well, for any k, we can find an interval smaller than this, such that this quotient is bigger, right? That's how lim sup works. So we consider this. So now I have a bunch of sets here that are all open. That somehow covers the point we're interested, but maybe they cover a bit more also for each k. But if I now take the union of all such sets, I should get a set which is relevant for my investigation here. Problem is that taking uncountable unions, I have no idea of, most likely don't have a countable amount of intervals here, right? Taking uncountable unions from a sigma algebra point of view is a bad thing to do because you can get basically anything by countable unions, uncountable unions, except if you deal with open sets, because the way topology is constructed, uncountable unions of open sets is fine, just like you can do uncountable intersections of closed sets. But you're only allowed to do finite intersection, right, of open sets. The sigma algebra, you can do countable on both sides. So there's a curious difference there. So anyways, from this, I form the set UK, which is equal to the union of all intervals in my VK. All right, and now this is also open. And now it's easy to see actually that the set E I'm interested in is the infinite intersection of the sets UK, right? Because I already said it, if X is in here, then it's gonna be, I mean, I can always find an interval down here, no matter where is K, that covers my X. Vice versa, if X is in here for every K, then actually you see that the lim sup here must be bigger than little a, and then yeah, in E. So this is it. The UKs are open, hence they are in the Brell sigma algebra. Now this is a countable intersection, so E is in the Brell sigma algebra. Cumulus erratum dominicus. Yes. Now, okay, let's get to the serious business here. Theorem 623, I believe it is. All right, so I wrote down the theorem here a bit sloppily. Let mu be the finite Brell measure on RD, then the mu, which, so we say that the measure is differentiable at the point x if the superior and the inferior derivative are the same, and the mu is going to be equal to that number at every x where it's differentiable and 0 elsewhere. Okay, so this is the function. This is the Radon-Nikodym derivative of mu a, so the absolutely continuous part of the measure mu in the Lebesgue decomposition. Right. As usual, once you have set up the necessary artillery, doing the main theorem is not all that hard. So it let's first assume that we just have the absolutely continuous part to worry about. So the idea here is that, okay, the lower derivative is always less than or equal to the upper derivative, right? So this is trivial. So the set of points where these two are not equal, we must have a strict inequality here. Oh, and by the way, so this is a bit of a proof that goes in several stages. So first, I'm going to show that these two are equivalent almost everywhere. Then I'm going to repeat the same argument to show that it's equal to f almost everywhere, where f is the Radon-Nikodym derivative. And then we throw in the it goes a bit slowly like that. But once you get this idea of how to prove that these two are the same almost everywhere, you kind of get the gesture of the rest as well. Right, so if mu is not differentiable at the point x, we have this inequality. And now we want to show that the set of points x that satisfies that has measure 0. Now it turns out that it is hard to attack this directly, but anytime you have a small gap, we used this several times, you can always throw in rational numbers there, and rational numbers are countable. So let's pick, here's the real line. For a fixed x, this is you have a complete value for this and another value for the superior guy, right? And then I can put here an R and here an S in between, which are rational.
Okay.
And what's the idea here? The idea is to use this inequality and then this stuff up there, the lemmas. And then that inequality and the lemmas, and like that get a contradiction, or not a contradiction, but something showing that the set of points x where we have this identity must be 0, right? Then you take the union of all R and all S such sets, and then that's a countable union, so you still have measure 0. So, okay, let's do x such that this is true. I'm going to define that as A, R, S, where R and S are rational numbers. Okay, so what does this inequality tell me? If I go up there and look, so I get that mu of A, R, S is strictly bigger than, or equal to actually S. Well, we can easily make it strict, but we don't need that. The point here is that the S lands on the right, on the lower side of the inequality, but S is bigger than R. Now we use the other lemma, the one with the lower derivative, And now we get mu a rs is smaller than or equal to r times Lebesgue measure of a rs, right? But r is the smaller guy. So if this is bigger than that, which is bigger than that, you know, it means that r is bigger than s, or lambda here is 0. So lambda is 0. And then, right, then the set of points where the radon, the set of points where these two are not equal is the union here. There's a countable union. So this is differentiable almost everywhere. Now, why is it equal to the radon-according derivative? So let's throw in a function. Well, the radon-according derivative is not that well defined, right? It's only well defined up to lambda almost everywhere anyways. So let's have this, all right? Turns out I forgot to put a bar on this guy. I hope you didn't notice. Anyways, now to get to the function f, here there is no such thing like this to say that we automatically have, you know, this is less than or equal to that almost everywhere. That doesn't matter. So this provides with more alternatives of how to set things up. But and here one has to be a bit careful, right? But it turns out we're interested in showing, you know, so f can be bigger than this guy and smaller than that guy and whatever. But as long as this doesn't happen except on sets of measure 0, we don't care, right? So what we want to prove is actually that the set of points x such that f of x is strictly smaller than that. This is of measure 0. And similarly, the set of points x where it's strictly bigger than that, it's going to be of measure 0. Because then we know that almost everywhere, my f of x is bigger than him and smaller than him, but that doesn't work out unless all three numbers are the same, right? So that's a bit clever. Now, how do we get that this, let's ignore him for a while, and then let's say, okay, so the set of points x where we have strict inequality here, then I can throw in my r and my s, and here instead of the lower derivative, I have my f. Okay, then the lemma up there still tells me that my mu rs is bigger than or equal to s times lambda of ars. But at the same time, this is the radon-according derivative. So if I want to measure mu of ars, I can just integrate f on this set ars. But that integral, I mean, what I'm integrating is less than r everywhere. So this inequality is also then true, right? And then I get, and I get that now this new definition of ARS as measure 0, the infinite union as measure 0, and therefore this inequality holds only at the set of measure 0, right? So then we get that now all three of them are the same. Finally, we have to deal with the singular part if there is one. Now we assume instead that we have a singular measure, and then we're going to just add our conclusions here. What do we have then? Okay, so this is our space, and then here's some set n, which is thin or not negligible, where the measure mu lives. And as we've seen in the example previously, I mean, here, the radon-according derivative usually, the differentiation of the measure is not possible. We don't care because that has measure 0. We want to show that the differentiation now is 0 almost everywhere. So what goes on this set doesn't matter. We're interested in what happens outside in the surrounding space, right? So take a point here, x. And let's say the radon-according, let's say the derivative of the measure or just a superior derivative, something happens here, then we need to show that that is a set of, that's a small set basically. So let's take the point x such that the superior derivative is bigger than or equal to 1 over n, for some n. Let's call that an. So if this doesn't happen for any n, then that guy is 0, right? And then the lower derivative is 0 as well, and everything is 0. So these are the bad points. Now, what is the measure mu of an? Well, this guy is bigger than that. So here we have 1 over n times the Beck measure of an. Aha, and I forgot to say that, okay, so we consider here x in the complement, of course, right? And now this guy here is 0. So this means that an has measure 0. And now you just do the union of all of those ans. It's going to have measure 0 still. And that will encompass all the points where the derivative is non-zero. So that has measure 0. And then this guy n has measure 0. So this guy is 0 almost everywhere, the derivative. And the wrap up is actually, now you think, oh, but how, I mean, yeah, it seems like a, a small thing. It could be a big thing to combine this. Now having both, but it's not, because you see that, lim sup and lim in follow additive rules. If you have a sequence, this is like analysis 1. So if you have a sequence AK and a sequence BK, and you want to look at lim sup of that, well, this is less than or equal to lim sup of your AK plus lim sup of your BK. And then with the lim in, you have the reverse inequality, right? So if the lim in here with the A case is equal to the lim sup, and the lim sup with the B case is equal to the lim in here, that I didn't write out, then these two are going to be the same. So differentiation, as we have defined it, when lim sup and lim in is equal, is additive, meaning that if this exists, and if this exists, then also this exists, right? And is equal to the sum here. So here we have the rather recorded derivative almost everywhere. Here we have 0 almost everywhere. And that's the end of the argument. Good. All right, so armed with this differentiation theorem, we can now embark on a series of just beautiful, beautiful applications, mainly on the real line, but first one in RD. So let's say you have some sets, sets can be very complicated, fractals and shit. Let's call it E. So here it is consisting of a blob and 3 curves. So then you can ask yourself, all right, so there's a bunch of points here, but which ones of them, deserve to be called really inside? Here we deal with an open set and lines. It's hard to paint harder sets, but you've got many sets which are infinitely. Just remove all the rational coordinates, for example, then you get a set with lots of holes in it. So if I take a particular point which is still in the set X, how much inside is it? Is it like really like embedded, or is it like a fringe point like this one of these lines? That's a natural question. So Lebesgue asked this and answered it. So one way to define that you're really inside is to consider cubes with axes parallel to the coordinate axis around it. And then I always work with intervals before, but so E of C in the book is the side length of the cube. You let that go to 0. And you demand that X is a point inside, right? And well, maybe I should write that down here then. No. All right. So one way to say that he's really inside is to look at this quotient. The Lebesgue measure of E intersected with the cube divided with the measure of the cube itself. And clearly this number is smaller than him. But if the limit here, as the side length grows smaller, is equal to 1, then clearly there's lots of points around which are also inside the set, right? So this is going to be called a point of density, a point X, such that this limit is 1, that's a point of density. And then if the limit is 0, then you call it, well, I mean, here it takes on supremum also. If that limit is 1, then it's point of density. If it's 0, then it is point of dispersion. I said limit supremum, actually limit infimum, if that's equal to 1. That's the requirement for being called a Lebesgue point of density. The definition here looks a bit different, but it's the same as the limit infimum equal to 1. All right. Anyways, you want to know how many points are point of density and how many points are not. And the point is that almost all points are points of density. And how do you see that? Well, you just consider the measure mu, which is defined by the characteristic function of E times the Lebesgue measure, right? This is absolutely continuous. So the differentiation theory we have says that the derivative of this measure equals the Radon-Nikodym derivative almost everywhere. But the Radon-Nikodym derivative is this guy. And for points inside of E, he is 1. Yeah, so the derivative of this measure, which basically is looking at that quotient, is equal to 1 almost everywhere in the set E. 0 almost everywhere outside of the set E. Yeah, so there you go. Now switching to the real line. So remember, we had this identification between measures and functions by doing this, right? And then the first observation here is a lemma, which says that if he's differentiable as a measure, then this guy has a derivative as a function. That's easy to check. Now, all right, so to study functions, we restricted ourselves to functions of finite variation, which is the same as requiring that the measure mu here has finite variation. We already covered that. And then also this function here becomes right continuous. So we need to require that he becomes right continuous. But we don't really want to deal with that. So first of all, if you have a function of finite variation that goes up and down, if this is your f, then we figured out that you can write f as f plus minus f minus, or basically this function here is the variation of f until the point x. Oh, how is it? So the variation of f was equal to f plus f minus, if this is some sort of minimalistic right? And then, yeah, so you do this one, you do var plus f, and then you get this, you divide by 2, that's how you define your f plus. And then it turns out now he is non-decreasing because the variation, yeah, this one, the variation has more variation than that guy, so it will always go up. And then you define f minus with the same, and then you can write any function with finite variation as a difference of non-decreasing functions of finite variation. All right. So having something like this, we can write it as a difference of a guy f plus and a similar guy f minus, and both of them are non-decreasing, right? But they might have some jump discontinuities, okay? And that's the problem, because in order to connect to this theory here, we need them to be right continuous, which means that the value here of the jump discontinuity needs to be equal to the limit here. We don't want that. We want to deal with more general just functions of finite variation. Now, so that's what and we're going to be able to do that. And that's where this lemma 6.3.2 is needed, because if you have something that's non-decreasing, that anytime you have a jump discontinuity like this, it has some finite distance, right? And if the total, I mean, the variation is finite, so it's gonna level out at some point, you know, there's some big M that sits on top of everything. So if I have a gap like this, it's bigger than 1 over some natural number, there can only be a finite amount of those for a fixed natural number, or for a fixed epsilon, you know? Because if there are so many gaps of size epsilon that will go bigger than the roof here, that's impossible. And then you take the gap to be 1 over n, and you see that actually there are just countably many gaps at all, countably many jump discontinuities. Now, so countable, we like that. So then you take a fixed point of discontinuity, where if your function f, you know, takes this value instead. All right, then you can redefine the function, take this value, and now you have two functions that we deal with, but they are the same except for countably many points. But from a differentiation or point of view, or for most purposes we want to do, a countable set of points, we don't care about it, right? That means you can replace your whatever non-decreasing function you have with a non-decreasing right continuous function. So, and once you have that, you can list it to just functions of finite variations in general. So that's kind of the blueprint, right? And the details here are not difficult. I'm just trying to guide you. Right, so if now this guy and that guy is right continuous, then we have this identity, and the differentiability of measures says that this derivative exists almost everywhere. In general, there is only a countable set of points if you don't have the right continuity. So either way, the thing is always differentiable almost everywhere. So that is the first theory. Well, the corollary says this. So if all right, and then there's a proposition 635 by Fubini. I don't know how interesting it is. It looks like some sort of Pepper-Levi for derivatives. I'm going to skip that one and go directly to 636, which is the Rolls-Royce version of fundamental theorem of algebra. So now, if mu is absolutely continuous, then we know that our f of x is equal to the integral from minus infinity up to x of some function little f, the lambda, where this is the Radon-Nikodym derivative. But now we also know that this is almost everywhere the derivative of the measure mu, and the derivative of the measure mu almost everywhere is equal to the derivative of him. So he is differentiable almost everywhere with derivative equal to that guy. So if we define it like this, f is in L1, then we get that f prime exists almost everywhere, and where it exists, it is at least almost everywhere equal to full f. Okay, and then there's a corollary saying basically the same thing. I mean, we can restrict here also. We don't need to be working on minus infinity up to some x, but we can start at some a and all points up to b, and then you basically get that f is absolutely continuous if and only if you have this formula. Still, all right, so if f is absolutely continuous, then the derivative exists. Okay, no finite variation, then the derivative exists almost everywhere. And we have this formula, yada yada. Right, no, we haven't said anything about finite variation, right? So, yeah, if you have absolutely continuous, so the point now here is why this text continues. It's like here we're given the function small f in the statement, and then we show that they're equal. Almost every derivative exists almost everywhere. But we would like some sort of intrinsic definition here, right? And then here they say that absolute continuity of f is the same as having this formula. All right, so then that's nice. You don't need to check finite variation that apparently follows. Right, that's an exercise here. That's the first line of the proof. Okay, but this is still unsatisfactory in the sense that if you just sit with big F and you don't have this formula, checking absolute continuity of a function is difficult. You remember the definition? It was something with for every epsilon there exists a delta, and then you have to have infinitely many small intervals and check some inequality. So it's you know, while this is very beautiful results, if you don't have small f to begin with, it's hard to. Now I see my colleague is waiting for me. I think it's hard to get to. I don't even know what I was going to say. That sentence at the end. Well, yeah. I have to cut it now. I'll be back and present the end here in a more concise way. Thank you. Tjena Arne. Jag som precis håller på att bli färdig. Kommer du att stå?
All right, so Arne kicked me out of the lecture hall. I'll try to round up here. So anyways, I was getting myself confused there. So what I was trying to say is that if you have a function big F, you don't know anything about its derivative. Since the absolute continuity condition is difficult to verify, it would be nice to replace it with something simpler, right? Like just saying that if it's differentiable almost everywhere, and let's say the derivative is integrable, for example, then you might conjecture that an absolute continuity follows, and then you get that formula that you can get back f by integrating its derivative. It turns out that that is false. So what's coming up in the book is, well, the final part there is first to do partial integration, like I've outlined earlier, that you can generalize it. So they've pulled this generalization to the end. I will just skip that. It's there, you can read it. And then in the end, they give conditions. All right, so if f is differentiable at all but a countable set of points, and the derivative is integrable, then you can reconstruct f. So, but that's, you know, it's not as beautiful, and, you know, in terms of usefulness, I don't know. I think this is more like trying to, you know, make the perfect painting, right? So that's as good as it gets. And that's the final results. So the conjecture there, I mean, if you just have the derivative almost everywhere and that one is integrable, that does not lead to the formula, you know, f reconstructed from its integrating its derivative. There are counterexamples to that, and that's in the exercises 5 and 6. So I recommend you to do those. A final remark, maybe just on chapter 6 as a whole, is that there is this alternative approach with maximal functions that I mentioned. And let me just briefly outline a bit what is the difference there, and I'll pull up the drawing board here. Hold on.
Okay, so let me explain a bit better, since we have some time left over in this class, the difference here or the alternative with the maximal functions. It turns out it's not so much of an alternative. In one variable it is an alternative, but in several variables actually you use the Vitali covering there as well. So it's more like an extension of the theory we've been working with. But anyways, so let's now just focus attention on the measure mu, which is f to lambda, so integrating a function f, which is L1. Then if you think about the derivative where it exists, it is the limit of quotients like this, right? So mu of I is just integrating over I against f, and then we divide with the length of the interval. And so you consider intervals that contain x, and you make sure that length of the intervals are less than delta, and then take a limit as delta goes to 0. So this gives a very intuitive connection with the derivative, so to speak, right? Whereas here, okay, so the alternative approach is to consider maximal functions, and the maximal function of a function f, like this, is the supremum of basically the same thing, but without this restriction that you should have a very small delta, or that some limit as delta goes to 0, which means that if the maximal function is big at some x, it doesn't really mean that okay, I talk all the time of derivative, but we have to connect this somehow to derivative of the function big F, right? Which we get from integrating this guy. Yeah. So let's now, well, first of all, okay, so for a general F with finite variation, we always decompose it. If F arises like this, then, or rather, if F is the integral from minus infinity up to x of little f, then this decomposition here in f plus and f minus is just integrating the positive part of f that gives you this f plus, which therefore is non-decreasing, and then minus, and here you take the negative part of f, and you get another non-decreasing function, right? Okay. So anyways, if we're interested in something like differentiability, oh, actually the maximal function here should have a modulus there as well. But if we're interested in a statement like f here is differentiable lambda almost everywhere, and the derivative is equal to little f, it suffices to prove that for f plus and f minus separately, right? And then we can, right, so that's the same as we can just add the assumption that f is non-negative. So let's add this here, and then we don't need to have the modulus here around our little f when we define our maximal function. And then the connection here with derivative of big F becomes more clear. So I'll erase this. Very little space on this blackboard, so I have to be a bit more economic. So now f is just the integral from minus infinity to x, little f d lambda. Okay, so now the partial goal here is to establish that we're going to establish that the maximal function is something which is in another space, which is called the weak L1 space. And then we're going to use that to see that the derivative of big F is small f almost everywhere. And then I will talk a bit more about maximal functions in greater generality. That's the outline. So, okay, so if now big F, now we can paint it, right? So big F can look something like this, right? So then here is the x-axis. This means that, all right, so here little f has some sort of bumps, right? This is little f, this is my big F. Now, if this limit here is, let's say, 1, it really means that the derivative of that point is going to be 1, so it's something like this, yeah? However, if this guy is bigger than 1, it just means that okay, so let's say that this is the point x. Is the maximal function going to be bigger than 1 here? I mean, so here the derivative is 0, but the maximal function, I mean, can we find an interval that contain x such that this quotient is bigger than 1? Well, then you just take a line with derivative 1 and do this, let it be tangent here and go down, yeah? So then now where it's going to hit the graph, if you think about the interval here between these 2 points where it leaves and where it reconnects with the graph. So integrate, so the length of this interval is here, and integrating f, little f, is going to be the difference between this point and that. So the derivative, so this quotient here for this particular interval I is going to be 1, and then x is inside it. So basically, we see that there are points x where this is bigger than 1, where you have very high derivative and where you have 0 derivative. So it doesn't give a very deep, you know, it's hard to get a feeling for the maximal function. But in one dimension, despite that they're very nice, so now I'm going to outline how we can avoid the Vitali covering business, at least in one dimension, if we're interested in just the differentiability properties of him, right? Because, okay, so in general, let's say that we have some constant a times x, so plus some offset. So this is m plus ax, that's this graph here, right? So m is, you know, constant where it, here's the y-axis, this is m, right? And then a is the slope. Okay, so we've figured out by now that the set of points, if we look at this set, points x such that the maximal function of f of x is bigger than or equal to a, that's the same as the set of points which are below a passage like this. Here, and then this is if and only if. So here, if I do a line like this with slope a, I'm never going to rejoin or cut through this graph again, which means that I cannot find an interval such that this quotient is going to be bigger than a, right? So then if I want to look for all the points where I have this inequality, I just have to go this, and then I just follow here, and, you know, imaginarily, you can like move a line with this slope around until you come to another point where it hits, yeah? And then you connect here again, so you get this piece. And then the last section is going to be here, right? Okay, so this is this set, right? So if I look at lambda times this, the measure of this set, okay, and then, so it's just a bunch of intervals, right? So if I multiply this with little a, I'm getting, well, the increase here, plus the increase here, plus the increase here, and of course, so all these increases is going to be less than the total increase of the function f, right? Which in turn is the L1 norm of f. Right. So then we can move this a and put him here. And now we have a sort of inequality, right? So here, this is the norm of little f. It's not so interesting. So let's just write it like this, c divided by a. So this is weak L1 definition. So the set of functions that don't need to be maximal functions, if you just replace mf with, let's call it g, right? So let me put a g here. So if g has the property that this level set of G, the Lebesgue measure of that is less than some constant divided by A, and if that's true for all A, then you say that G is in weak L1. So this is then weaker than being L1. And how do we see that weak L1 and L1 are not the same? There's actually a very simple example. Just take a characteristic function between 0 and 1, right? And then you think about, okay, so how do I maximize this quotient here? So my f is the characteristic function of 0 to 1. Then, right, so if you have an x here, you want to maximize this divided by that. And you do a bit of math, you see that the interval should start here and end at 0, right? So then you get 1 divided with actually the distance of x. So you get, except for near 0, so at least on, beyond 1, you have that the maximal function of this particular f for x bigger than 1 is equal to just 1 over x, which is not L1, right? So the weak L1 is a bigger space. Okay, so I raised a bit here. So how now do we use this to prove that the derivative of f is always small f? Well, if f is a continuous function, then the fundamental theorem of analysis already tells us that, we want to establish this f prime of x is equal to little f. So if f is continuous, we know that. And we also know that continuous functions are dense in L1. So here's the trick. What we can do is so you start with an f in L1, and then you take some sort of phi, which is continuous, right? Such that f minus phi is less than some epsilon. Now, this phi gives rise then to a function big phi, which is then obtained by just integrating small phi, and then we can consider f is equal to f minus big phi plus phi. Okay, so the derivative of him is equal to small phi everywhere, and now we just have to show that the set of points where this derivative, when this function is misbehaving, somehow is very small. But okay, so I can't do the details because it's going to get too much, but I can just give you a hint. So then I have here the knowledge now that the maximal function of f minus phi is smaller than or equal to this, right? In L1, which is epsilon. Yeah? So basically, here I know the derivative exists, and about this guy, I know that the set of points where the maximal function is big is very small, right? So I can make it as small as I want. And you play with this, and then you can derive that actually, since this epsilon can be made as small as possible, the set of points where big F is not differentiable has to have measure 0. I'll skip the details, but maybe it can be a good exercise for the advanced exercise. Okay, let's put it like that. So, okay, that's a way to get a little bit differentiation theorem, just with this beautiful observation in the bottom. This is somehow closely connected to something called the rising sun lemma. You can read about it in Wikipedia. Okay, so that's about the alternative approach. Now, since we started talking of weak L1, let me just outline a bit the theory of maximal functions in more generality. So weak L1 is this. A function g is in E weak L1 if and only if you have this. So what we now know is that, okay, f is in L1 implies in one variable, at least we know that then the maximal function is in L1 weak. So it turns out in several variables, this is also true. It's just that now to prove it, you can't use this, this argument I just erased. It very much relies on the x-axis having like a right and a left direction, right? But in two variables, you have just many directions. So that breaks down. And what I read about this is that you usually use the Vitali covering when you want to prove a statement like this in several variables. Now, this connects to, then you can start asking, okay, but if f is in LP, does it then follow that it's in LP weak, or how we now would like to define that? We have to think about that. It turns out it's even better. So if you put L infinity, then without having any weak something, you also get here L infinity, right? Because you integrate something which is bounded, the integral is less than the bound times the length of the interval, so then you just so the bound for f in L infinity will the maximal function will have the same bound. Okay, so now we know that if f is in L1, then the maximal function is in weak L1, and if it's in L infinity, then it's in L infinity. And some of these are the extremes, right? So here's 1, here's infinity, and in between you have all the possible p, right? And this is beautiful, but very deep theorems about something they call interpolation. Interpolation means basically it's used in engineering. So if you have measurements at 2 points of a function and you just want to figure out how it looks in between, then you can do polynomial interpolation or whatever. But in this area of analysis, more pure mathematics, interpolation means something completely different. So it's a way to go if you have a statement that, like here with 1, and then with infinity, then for a p in between, you can actually lift this with a process called Marcinkiewicz interpolation. Marcinkiewicz is a Polish name. So actually you can have weak here and weak there, and then the fascinating thing is you get stronger result for the point that you interpolate for. So the conclusion is that if f is in LP, then actually f, the maximal function of f, so in LP, so you don't need this weak or whatever. I haven't defined it yet. I haven't thought about how to define it. But the fascinating thing is, like, if you have a weak type estimate in the extreme side, then you get a strong estimate or theory of the interpolated point here. So beautiful theory. Anyways, that finishes chapter 6. So next time we will do, where's the camera? So next time we will do chapter 7 and then 9 and 10. And from now on, I will stop lecturing all the details, right? So from now on, I will be more expository in my lectures and try to give you an overview of what's going on and what are the key tools you need there. So in terms of my course, if you're following my course, for the oral exam, I will test in detail, just like first part, knowledge of the proofs, the main proofs in chapter, the material we have covered. But from now on until the end, I just expect you to have like an overview idea of what's in those chapters. And then your assignment, okay, let me get back about the assignment, but I think it will be to make like a detailed exposition of an area of your choice here. Let me double check that before I will come out with more information on that particular topic. Okay, so that's the plan. Thanks you for today, and see you next time.